Hi everyone, my name is Ella. I'm an algorithm developer at Twiggle. I'm really excited to be here. I want to tell you today about a project that I've been working on, which actually started on my first day at Twiggle when I came to my boss and I asked what am I going to be working on, and I thought he was just going to give me a small, irrelevant task. And he said, well, you have to create knowledge of all the product types in the world. And I was thinking, okay, that doesn't sound small, and it really isn't. So after a while, I'm here to tell you about Twiggle and about my project. So our mission in Twiggle is to connect shoppers to the product they want to buy through a technology that understands them. We have a few products at Twiggle. We have a search enhancement product, we have catalog enrichment product, and we also have a super cool voice app. So you can imagine going around your house saying, oh no, I forgot to buy milk, and your phone will reply, added your favorite kind of milk to the cart. What? So I think that's pretty cool and forward. And what's common to all these products is that they all require two things. They require natural language analyzer, which understands the different parts of the language. And I will not be talking about that part today. But the second thing that we need is knowledge, which is represented as the universal product ontology. Now, if you don't understand what I mean by knowledge or ontology, that's okay, because I'm going to explain that right now. So our ontology in Twiggle includes a few things. The first one is the knowledge of product types. And what I mean by that, if you have two products, then if they are interchangeable, then it means they belong to the same product type. Let me give an example. Let's say I go to the supermarket and I want to buy Dijon mustard, but they just ran out of it, so I might be disappointed. But I guess I'll just go ahead and buy American mustard instead. So that means that they both belong to the same product type. They're both mustard. Now, what's a little bit more complex is that the different product types can have relations between them. So our mustard can have a certain relationship with the mustard spice. As humans, it's kind of intuitive to us to think, well, they probably share the same main ingredient, they might have a similar flavor. And on the other hand, the mustard can have some kind of other relationship with the ketchup. They're both condiments, they can be used for the same purpose maybe. So they have that relationship, and they have a whole other relationship with the mustard spice. So this is where it gets a little bit tricky. And for us, again, as humans, it's pretty intuitive, but for a computer, it's going to be much more complicated. The third part is properties. So my mustard can come in different packages, can come in a jar, can come in a bottle, can have different sizes, can come from different brands. And the fourth part, which is also a little bit tricky, is constraints. Because if I have a yellow mustard and I have a brown mustard, then you might be able to think, okay, let's combine the knowledge of color with the knowledge of mustard. But actually, we cannot do that because there's no such thing as a green mustard or a blue mustard. So we have to constrain that in a way. And we also have to know that a yellow mustard is exactly the same thing as an American mustard. And well, I just spent the last few minutes talking about mustard, but there are thousands of other product types in the world, and each one of them has just as many properties and constraints and relations with other product types. So by now you're probably thinking, okay, this might be complicated. And this is where I come in. Well, my goal in the project is to automate the process of knowledge generation, and I'm going to be doing that by following users' logic. All right, I want to create knowledge in the way people are actually searching for. So if a tomato is actually a fruit, I might not want to create that kind of knowledge because people don't search that way. And another important thing is that I want to keep human in the loop. We have very talented domain experts in Twiggle, and I want to keep them in the process because I don't think I can reach their level of understanding and their level of building the knowledge. That's why I want to create suggestions for product types based on user data, and I want to give these suggestions to our domain experts in Twiggle. And the last assumption, the last guideline, which I'm going to go back to it later, is that it's going to be easier for a person to split product type than to join them. So if our domain experts have to look at all the different product types and then think, oh, maybe this is like this, maybe I should connect them, it's going to take them longer than just looking at a single product type and maybe need to split it. And I will go back to it. All right, so how are we going to do it? How are we going to create that kind of knowledge? It's complicated. So I have 4 main steps in my algorithm. The first one will be to create a graph containing many, many products. Then I'm going to embed the graph. I'm going to assign every node with a vector, and I'm going to cluster it and give it a name, every cluster. So you can think of a huge, huge, huge graph containing probably, hopefully, all the different products in the world. And then I just want to split that graph into the different product types. I want to say this part of the graph is a cucumber, this part of the graph is a tomato, and hopefully it will work. All right, so let's dive into each one of these steps. All right, so like all good things in life, my algorithm starts with a graph. And the first information my graph has nodes, which are queries and products, and it also has edges connecting them. And the first piece of information which I'm putting in the graph is real users click. And so if someone looked for feta and he clicked on the product, then I'm making that connection. And here, the thickness of the line indicates the number of people that have made this click. All right, so if the line is thick, it means that many, many people clicked on that product after searching that query. And right, the second piece of information that I'm putting in my graph is results from search engines. So in Twiggle, we created automatically many, many queries that went to search engines, and we saw what products we're getting in return. So I'm also putting that in the graph. I'm also connecting products which are in the same category in the website. And I'm going to connect queries based on external ontologies. So if I have an external ontology which told me that feta and brie are both types of cheese, then I'm making this connection. And at this point, you might ask yourself, well, if you have an external ontology, why are you putting that much effort into creating your own? And the answer is that it's just not fitting to our needs. So for example, an external ontology will tell me that a tomato is a fruit, but I don't want that kind of knowledge. And at this point, you might ask yourself another question. If I'm building the graph this way, then how am I getting one big graph containing all the products rather than many, many, many small graphs, each one of a product type? Because you wouldn't expect there to be a connection in the graph between cheese and a garbage bag, right? So the answer is, and I bet you guys will all know what I mean, data is messy. So in users click, sometimes people click not on the product they search for. Please don't do that. And also, products in the same category can also be kind of confusing because we can have categories like sale or Christmas that will contain many types of products. Yeah, but it's good. This is where it gets interesting. All right, so actually, it looks something like this. This is just a small piece of my graph. And again, I'm building a huge graph of products, and I want to divide them into the different product types. Now, if you want to perform a clustering algorithm on this graph, then I need vectors. I don't need nodes, I don't need a graph, I need vectors. This is why I need to embed the graph and make every node a vector. And this is where I'm using node2vec. This is a good time to pause and say thank you for the meetups. Because about a year ago, my colleague was here in a meetup and he heard about node2vec, and this is how we got the inspiration for our project. So thank you, our meetups, and good things can come out of it. And thank Elior, of course, for his lecture. And back to our algorithm. So I want to embed the graph and turn every node into a vector. I'm going to be doing it with node2vec. And the way node2vec works is kind of cool. It is based on word embeddings. So in the word embeddings, we're turning every word into a vector, and our input is many, many, many sentences of the language. So when I'm doing it for the graph, I have nodes and I want to turn them into a vector, and so my input is going to be walks in the graph, okay? So if in a language, sentence is a sequence of words, then in a graph, walk is a sequence of nodes, as you can see here. Now, since I'm not going to be sampling all the walks in the graph, because you've seen how big the graph is, I'm going to sample the walks. And so the way I sample the walks is crucial for the output of the algorithm. And I can sample the walks in a more outgoing way or more localized way, BFS versus DFS kind of. And it can be controlled with two parameters, P and Q. I can also control the number of dimensions I have, the length of every walk, and the number of walks I take from every point. And we actually tune these parameters using a small tagged set. All right, so once we've done that, we had a graph, now it's gone. We have a bunch of vectors, we can cluster them, that's great. And I used the dbScan algorithm. I used it because it doesn't require prior knowledge of the number of clusters, because I don't know how many product types I'm going to get. And what it does require is two parameters, the maximal distance between 2 points in order for them to be in the same cluster, and the minimum number of points per cluster to be considered a cluster. And all the points which do not answer these criteria are just being classified as outliers. All right. So I got my clusters, and now I'm going to go ahead and give each cluster a name. I'm going to be doing that by choosing the most frequent n-gram out of all of the titles of the products and the queries in a product type, in a cluster. And the rest of the n-grams will be used as suggestions for synonyms. And my last step is going to be to connect product type, to connect clusters, which I've given them the same name. Why am I doing that? As I've mentioned before, it's going to be harder for a person to join clusters, so I want the algorithm to try and do it instead. If I have clusters which need to be grouped together, let's give that to the algorithm rather than the person. All right, so hopefully by that point, I got my clusters, which are the product types, and each one of them will contain products, queries, a name, and suggestions for synonyms. I think it's time we see some examples. So I ran the algorithm on the furniture domain, and I got many product types, as you can see. If you would have to think of all the different types of furniture you have in your home, I'm sure you wouldn't have gotten to that list, and there are things in here which I didn't even know existed, but our domain experts say they exist, so I believe them. And what's cool is that we're able to capture a lot of synonyms. So for example, the product side table can be called in many different names, like accent table, sofa table, pedestal table, and on and on. And if a person had to go and look for all of these synonyms, then probably would have taken a long time, but here we just got it like that from the clustering. So I think that's kind of cool. We also ran the algorithm on the fashion domain, and again, many product types. I wouldn't have thought of them in like a million years. And we actually found that the clustering helps us to solve problems of disambiguation. So for example, the product on your right has many product types in its name, so it would be hard to tell what it is exactly. You can see from the picture, but and so here we know it's a slipper because it got clustered together with the rest of the slippers. Cool. And also the naming algorithm turned out to be pretty useful as well. You can see here many products, and they have different kinds of names. And the algorithm decided to call them all face wash, because I think it's a good name for it. And yeah, so we were able to create knowledge at scale. We took tens of thousands of products and we grouped them into different product types. And we were able to do it with, I think, more than distant percentage of accuracy. So for example, in the fashion domain, we took 60,000 products and we grouped them to 65 product types. So it's roughly 1,000 products per product type. And out of these 1,000 products, 80% really belong there. And I think it's a rather big task that we're able to accomplish. And hopefully, I've managed to convince you that creating knowledge is a hard task. And this is exactly what we do at Twiggle, where we combine complex algorithms with human insights. And I hope you enjoyed the talk. And if you have any questions, I'd be happy to answer.
The data was imbalanced?
Sorry?
The data was imbalanced or balanced?
Towards?
In terms of classification, 0, 1. In terms of which type it belongs.
The data, well, our data was queries and products. So we didn't know what are the types of the products. We had to create that understanding. Yeah, it's imbalanced. Right, so that's a great question. The question was how do we deal with the understanding of attributes? Because I mainly spoke about understanding product types, and attributes is actually a very hard task. So, well, we have a few ways of dealing with it. We're currently building an automatic flow to deal with it, but it's a hard task. I can tell you that.
How will you handle the input of new products?
Right, that's a great question. How will I deal with the new products? So the answer is that whenever I get a new set of data which contains maybe more products, more queries, more categories, whatever, I can always just insert that to my graph and just do the whole algorithm once more. Yeah. Yeah. Well, it just the algorithm just takes like a few minutes to run. So I can whenever I need, I can just do it again and find more product types given any new information that I receive.
So it only takes a few minutes to handle all the data?
Well, it takes a few minutes because I'm separating the data to domains. But even if I wouldn't have done it, it would just take, I don't know, maximum an hour or something. Yeah.
How can you tune the other parameters for DBScan?
You're right. Right. Yeah, I forgot to say it, so thank you for asking. For the clustering algorithm, the DBScan, I also tuned the parameters with a small tagged set, but we also kept checking the sanity of the parameters. It's very crucial. For example, when we looked at the minimum points which need to be clustered together to be considered a group, the minimum points per group, then we thought about how many catalogs we have and how many products we would expect for a product type to be in the catalog. I mean, I would expect, okay, there will be one tomato in every catalog, so this is the minimum number of points that I need per cluster. So we kept connecting it to the real problem. Yes?
You said that the user clicks, they affect the width of the edges. What is it affecting after all? The random walk maybe, or?
So, okay, I will answer that. In my graph, the weight of the edges is taken from the number of clicks, and actually the rest of the data which I'm inserting is getting a rather low weight because I want to keep. I want to make the user's data as much important as it can be because it's the most crucial part of the data. And once I'm putting the weights inside the graph, then Node2Vex takes that into consideration and the embedding is done accordingly because the weight of the edges is very important for the embedding of the graph. Yes?
Give an example of how much the result of the supposed to get the product, how much the new result is consistent with the previous product,
Okay, so given a new product that we have, how is it affecting the algorithm?
The results of the previous category.
Yeah, so it really depends on how many new products I'm putting in the graph because it contains hundreds of thousands of nodes, so probably one or two products will not be much of a difference. But if I'm putting inside if I'm putting a new source of information, it has a lot of many new products and product types, then it can change, of course, the result. But we always we check does it need to be changed? Does it need to be different? Are we putting new product types? Are we expecting it to be any different? So, yeah. But the more data we have, it's better. Yeah.
How sensitive are the categories
with respect to the walks themselves. If you run it 2 times, 3 times, you end up in the same category because you have a random walk at the middle.
Right, so we have a random walk, and you're asking how
sensitive are the categories?
How sensitive?
Do you end up with the same categories or?
So I think it really depends. Okay, the amount, like, how would I say? The change in the categories when we take different sampling of the graph depends very much on where you look in the graph, because some parts of the graphs are more in the graph are more dense. Yes, thank you. Are more dense, and so it will affect them a little bit less. And there are some parts of the graph where we have maybe little information, a little bit data, so they are they're very sensitive to changing in parameters. And these are the parts that we always try to improve, to put in more data, to make it more robust, and to improve all the parts that are not that dense as others. Yeah. All right. Thank you, everyone.